discussion of the events 4.8 to 4.12. I want to talk about three presentations. This is part three, excuse me. Three presentations. I want to start with a presentation by OpenAI. Jason Wei and Hyung Won Chung discussed large language models and some of the intricacies, some of the ideas, some of the things that they learned. Very interesting. I'm going to talk about those things. And then two presentations which are related. One is Aaron Dollar. He is a professor, I believe, at Yale, Mechanical Intelligence and Robotic Manipulation, and Kui-Jing Zhou from Seoul National University, Nature-Inspired Designs. Both presentations are, mechanical intelligence. They're about mechanical intelligence. They're about the design of, let's say, grasping, or walking, or bending, or any kind of physical activity which has a biological inspiration under it. So that means that, like in the words of Kui-Jing Zhou, he says that typical robots, they work in structured environments. So they have very clearly predefined action spaces. And in order to put them in unstructured environments such as factory floors or self-driving car and traffic, we need sensors and actuators, and we need some sort of algorithm that can translate the sensors input into actuators and states and act accordingly. So that's additional robotics. So the question that both Aaron and Kui-Jing Zhou ask is, can we have mechanical intelligence without sensory input, without algorithmic solutions, where just by the nature of touching and forces and counter forces, Newtonian physics, if you will, or even quantum physics, just basic physical relationships, geometries, forces, they can act on each other and hence, develop, trajectories, right? I mean, it's not very different with humans. This is, I just discussed in the previous episode, Moravec's paradox with large traffic scenarios. Like when you have two humans that act together, I argue you could almost, in many situations, it's, even like having sex or something, it's almost, it's mechanical intelligence. Like you don't analyze algorithmically, or maybe you do. Maybe mechanical intelligence in the end is just another type of intelligence. But at least from a design and engineering perspective, when we build mechanical solutions for grasping, for example, Kui-Jing Zhou, he showed in his presentation how you can have, birds when they land, they use the force to then grasp towards, let's say, a branch on a tree. He's using origami solutions that can be folded and unfolded to withstand massive pressures. Those are physical forces that act on each other. Architecture, an arch. What is an arch? Arch bridges that were, introduced by, I believe, Ottoman architects, and then brought to Europe. And you go to Venice, you see a lot of arch bridges and things like that. Where did they come from? What is an arch? It's mechanical intelligence, right? How to keep something from collapsing. So those kind of things. I think Aaron Dollar actually talks about one of his PhDs. He went to work for Tesla and he built a prosthetic hand. So he literally has built a hand that can be used by humans who are unfortunate not to have the availability of a hand. And the same thing the same concept could be applied to a robot. Again, you can solve grasping through sensor input and algorithms, but maybe you can add in mechanical intelligence. So I want to talk about those two presentations and also about the presentations, large language models. This is not even a podcast. It's April 12, 2024. This is Delco. For the year, we're down 19.2%. The market's up 6.8%. We're underperforming by 26%. The first presentation is an OpenAI presentation. Jason Wei and Hyung Won Chung, they're both researchers at OpenAI. Jason talked about some aspects of LLMs that I believe are all really interesting. One is the multitasking. So the way LLMs work is they learn several tasks one after the other. So there's the task of filling in blanks. There's the task of grammar. There's the task of summarization. Those are tasks that they learn subsequently. So they learn one thing, then they learn the next thing. So there's the multitask aspects of large language model learning. Now, why does scaling work? That's another one. Scaling actually works. And more compute generates more learning. I believe it's related to the first concept of tasks. So if you want the anatomy of tasks, it's just different types of relationships between the data that the model has learned, and the more relationships you learn between the representation that you memorize, the more you learn, and the better. So if you learn how to fill in stuff, and then you learn how to put commas, and then you learn how to summarize stuff, those tasks require more compute. DNNs learn basic representation of reality and then combine them through compute and memory. That's why scaling works. Another interesting thing is that overall loss declines with the increase of compute, but some tasks get better suddenly. So it's not everything is smooth. And that's because some tasks, the loss, which is a measure of how good the model is by declining loss, which means you're getting much better at predicting whatever you need to predict relative to the ground truth, and that minimizes the loss. So the loss goes down in certain tasks very fast, in other tasks very slow. On average, an aggregate, the loss comes down gradually, but certain tasks loss comes down much faster than others, and therefore in some situations certain tasks you learn kind of suddenly. And then there's inverse scaling, which is really, really fascinating, which just means that in some situations, actually, a small model can do something, a mid-sized model can not be very good at something, and then a large model can be good at it again. This, to me, is a little bit, it's kind of a tricky situation. It's a tricky situation in the sense that it reminds me of the Moravec paradox in traffic scenarios, where you have small number of people that make it, relatively easy to predict interactions, medium-sized, relatively difficult, and then large-sized, again, easy. In this case, it's a little bit different, but the concept is similar. Like, I guess when you have a lot of data, then you have a lot more transfer learning, and also, I guess, less degrees of freedom because of the law of big numbers. And when you have medium-sized, certain things can become relatively difficult to do, while when you have small-sized, again, certain things are very easy. I think this is something that I need to do a little bit more work on, but Jason spoke about this. Hyung Won Chung spoke about a sort of general recipe for AI. What works is develop progressively more general models with weaker model assumptions. So you want to generalize on the one hand and have weaker assumptions. So less hard coding, less, ground truth, a priori stuff, none of that. Data-driven, general, data-driven. Focus on data, more compute, more data, and focus on the data. Don't focus on the priors. Structure matters, but structure can be natively developed. In other words, if you add more compute to something, you create structure. Structure is important. Structure is, the representation of, latent representation of reality. This goes back to, this is, even Douglas Hofstadter in I'm a Strange Loop talks about this. Like you you need some sort of symbolic representation of reality, and that's where Douglas comes. His strange loop is when you build these symbolic representations of reality, and then you relate them to yourself. That's when you build the I. So you need structure. We need structure. Structure is important, but you don't want to put it a priori. He was also talking about transformer architecture, and I thought that was interesting. In the transformer architecture conversation, you have this decoder, encoder, decoder type conversation. And I think what he said here is actually very intuitive, which is decoder only is really the way to go. What does that mean? It means that we have data comes in some sort of form, and we have to represent that data. So we have to represent it let's say in vectors, right? And if the data coming in is represented in vectors, and then the model itself has representation in vectors, then we have the same sort of structure, and then we can do something with it, compare, run some sort of algorithm on it, and then decode the result or move it into a higher abstraction, and then learn from that. So I think in that sense, decoder only is, according to his presentation, is the way to go. Now, I think with all of these things, I think we could be up for like a completely new architecture next year or a year after, because the learnings are so interesting and dramatic that you have serendipity, you have well, what I'm saying is I don't want to be so sure about the fact that transformer architecture is the future and the decoder only is the future. That's all I want to say. But I think to summarize this presentation by the OpenAI people, it's just really fascinating to see how these models, it's like neuroscience, like we're learning about the way the intelligence works, the generalization of intelligence, and it's very fascinating. Now let's get to the other two presentations here, and I want to combine them and particularly talk about Kujin Zhou's presentation, bio-inspired materials, bio-inspired robotics. So we have, wearables, prosthetics, bio-inspired robots, soft robots, deployable robots, 4D printing. The whole idea of both Aaron Dollar's and Kujin Zhou's presentation is that we have intelligence in mechanics, so in physics, without specific algorithms, sensors, and actuators. Just pure physics, pure, let's say, grasping can be understood as a forces against each other type of problem. And if we design, let's say, a hand that takes advantage of certain forces that act against each other while the hand is doing something, we can then have solutions that are computationally much more efficient and also much better. So, for example, there's this situation with the bird. The bird, when it lands, its feet grasp automatically through the force of the landing. So it uses the force of the landing as an actuator to grasp, and that's mechanical intelligence right there. You don't need math or any kind of actuator or anything like that. And I think this reminds me a little bit also, let's say in game theory, we almost have the same type of approach where we say, okay, two agents act on each other based on logic, and we can kind of infer from a priori states where this is going to end up. So in that similar sense, I think, if you will, what both of these professors are doing is kind of game theory with physics. Like we know the laws, the forces, the relationships, dynamic. If we build an origami type system that unfolds and keeps pressure away, or holds pressure or attracts pressure or whatever, we can iteratively play that game, if you will. It's almost like game theory, where we use the forces and then see how it ends up. I mentioned the prelude, the bridges, let's say the arched bridges in Ottoman architecture. That's mechanical intelligence. grasping again, fingers like we humans, we have the thumb. The thumb is a finger that is opposite of the other fingers that helps us do things, whether it's grasp again, hold something, the fact that we walk on 2 feet, there's a lot of mechanical intelligence involved in our being, and I think it's very encouraging to see Aaron Dollar talk about one of his PhD students actually going to Tesla to work on the humanoid robot. I think humanoid robots or robots in general, this new generation of robots will have to incorporate that. It would be a shame if they didn't. And then we have traditional robots, they work in structured environments, and the new types of robots, they work in unstructured environments, and unstructured environments imply that we need a better way to interact with nature, and that can happen through sensory inputs and algorithms and translation functions and control theory, or it could also happen through mechanical intelligence. I think this is the big takeaway of these two presentations. Thank you.